in the last lecture I was just trying to correlate some of the factors that we use to describe dispersion of light or group velocity dispersion, and those factors were the phase velocity, the group velocity, the wave vector, okay, all such things, the phase of the different wavelengths. That is what I was trying to do, and it is important to know these correlations between all this, because if in order to design a system which gives you this kind of the dispersion, when the medium, we have to understand the medium and the way it presents itself to the light pulse that we are talking about. We need to know all these correlations. Okay. So, I spoke about the prism which gives you the dispersion, I spoke about the optical fiber which gives you a dispersion, then I spoke about the grating also which gives you a dispersion of light, and all these will be used in our system of ultra short pulse amplification. So, let me go back to this. So, here is Vp, Vg and k omega, which is a function of frequency and a function of the refractive index. Now, the pulse travels in a medium, say we are in a medium of length L, and there is a change in phase. Okay. Okay. So, here what I talk about is the phase at that instantaneous time t, while here I am saying what is the change in this phase itself, which is okay, what is the change is called phi. Phi will depend obviously on the length it travels, the phase will change depending on that, the phase between the different wavelengths will change. It will depend also on the refractive index of the medium, and the refractive index on its own is again dependent on the frequency, and c is the velocity of light. So, you can understand the phase change is equal to omega n omega L by c. Now, group delay of the pulse is called t omega. Now, this is a new thing that I have introduced, grouped delay. Group delay means, see I have given it as a function of omega. That means, each of these frequencies get delayed. You know, each of these frequencies are getting delayed, as I have shown in the previous slide. So, I will call it as t omega, it is obviously function of omega, and this is the group delay. Now, t omega should be equal to length traveled divided by the velocity, L divided by Vg, it is part of a group. So, this delay will obviously depend on the length travelled in my medium, say a fiber, okay, and that is equal to L by Vg. Now, d phi by d omega, that means the change of this phase with frequency, with each of these frequencies which exist, is equal to n omega L by c. Okay, I have just taken the derivative with respect to this here, d phi by d omega. Okay. So, this omega part goes, and here what you are left over with is n omega L by c. This has the dimensions of time, as you can see. Okay. C is centimeters per second, centimeters will cancel off with L, and per second will remain. Okay. And refractive index of course is a dimensionless quantity. So, d phi by d omega is equal to n omega L by c. Then t omega can be equal to t, this has the dimensions of time, and t also has the dimension of time. So, the group delay t omega is equal to d phi by d omega. So, if you know the change in phase, then you will know the time delay also. So, this is a very important equation. Then t omega is L by Vg, we have seen here t omega is L by Vg. is equal to L dk by d omega, okay. Because Vg, remember, Vg is d omega by dk, L by Vg will be L dk by d omega is equal to d phi by d omega. Okay. So, these are the relationships between the phase and the time and the delay, and they will be used. It is better to know all these formulae, so that all these equations, so that you can use it later on. Now, we want to know the spread in propagation time. That was our original aim. Okay. How to get about this chirp, and what is the spread in time that we have, because of the involved frequencies. Okay. We must know that. So, here the spread in time, I call it as delta t, is equal to d by d omega. Of course, the spread in time is a function of omega. So, d by d omega, t omega, that is the group delay, t omega and delta omega. Okay. This equation seems fine. If you see, delta omega and d omega will cancel each other, and you will have the dimension of time here, and you have the dimension of time here. Okay. So, this equation looks perfect. So, delta t becomes d by d omega, and t omega I just substitute from here. Okay. So, it is L dk by d omega and delta omega. Dispersion is equal to delta t by delta omega. So, I just bring this delta omega on this side here. So, it becomes delta t by delta omega, which is called the dispersion. Okay. It is related to the group velocity dispersion, but dispersion by itself is slightly different from group velocity dispersion. It is definitely related. So, I am talking in terms of the dispersion of light. Okay. The dispersion of light is given by delta t by delta omega is equal to L d square k by d omega square, okay, which I have done here, which is here, is equal to d square phi by d omega square, just substituting here and here. So, this is an important expression. Okay. So, I can find out the spread in propagation time if I know d square phi by d omega square. Just multiply by delta omega and I will get the spread in time. Okay. The exact picture, the exact length in the temporal domain, I will know that, okay, from this dispersion expression. Dispersion is often defined as temporal pulse broadening per unit bandwidth. It is easy to see here, okay, and it is easy to understand also that depending on the bandwidth, your dispersion will either increase or decrease. Okay. Now, let me here. GVD is a characteristic of the dispersive medium. You agree with that? That describes how the medium affects the speed and duration of light traveling through it. Okay. So, this is a nice way of describing GVD, and you understood this meaning from the previous two slides. Okay. So, GVD is a characteristic of the dispersive medium, that is known, and it describes how the medium affects the speed. Okay. So, that is why group velocity dispersion, velocity comes into the picture, okay, of light traveling through it. GVD is specified in terms of femtosecond square length. See, GVD is affecting the time, that is why you have this femtosecond square, and the dispersion obviously depends on the length the time the pulse travels. So, it is per length. So, femtosecond square per mm. Oh, this is some unit of group velocity dispersion. Just to give you an example, GVD of fused silica is 35 femtosecond per mm at 800 nanometer. Okay. And GVD of fused silica is minus 26 femtosecond per mm at 1500 nanometer. So, it is wavelength dependent. At a particular wavelength, your group velocity dispersion is this, and at a different wavelength for the same material, the GVD is this. This is also, you can understand it, because that same medium presents itself to the light that is coming in, and the refractive index of that changes. For different wavelengths, the refractive index is changed. So therefore, GVD is also changed. So at different wavelengths, these are generally referred to as the central wavelength of that pulse or the light beam. You know, there is a bandwidth, of course, attached to this 800 nanometer, and there is a bandwidth attached to 1500 nanometer. Okay. It's just to note that the GVD of the same material can be different depending on the wavelength that you are using. Okay. Then there is, now when I say this positive and negative, okay, that will be described here. When d square k by d omega square is greater than 0 and d square phi by d omega square is less than 0, this is positive and this is negative, then it is called normal dispersion and positive frequency chirp. Okay. And if it is d square k by d omega square is less than 0 and d square phi by d omega square is greater than 0, okay, this you can calculate from the formula which is there in the previous slide. Then it is called anomalous dispersion and negative frequency chirp. Okay. So when I put this negative value, that means at this wavelength some anomalous dispersion is taking place, while at 800 nanometer it's a normal kind of dispersion. So it is positive here. Okay. So these are the definitions which you should keep at the back of your mind when you are trying to devise a system for further amplification. Okay. Now I go back to this This is the ultra short pulse. Again, the same picture: stretching, amplification, and compression. So what was the first paper? The paper that described the chirp pulse amplification process. They used a fiber here, fiber to stretch the pulse or to get the GVD that they wanted. So you increase the length of the fiber or reduce the length of that fiber, depending on that you will get the amount of GVD you require, or finally the amount of stretch in the temporal profile that you require. So in that first paper of 1985, they had done an experiment with the fiber. Okay. So here I have the oscillator which is giving you the seed pulse, which has the seed pulse has all that perfect parameters that you desire. It should have a nice cross section Gaussian profile in the space region. It should have a short pulse in the femtosecond range, and obviously since it is in the femtosecond range, it has a very large bandwidth. Okay. These are all the ideal parameters which will come out of the oscillator. Okay. Now these ideal parameters have to pass through the fiber, pass through the amplifier, and it should be recompressed back, and all those parameters should be conserved. Okay. So in that process, the first step is the fiber, where I am getting the stretching. After it has been stretched, it goes to the amplifier. And again there is an amplification process that is taking place. Okay. So here I have just shown rods like this because I am thinking of ND glass rods. So till now I have thought ND glass is good. Now after this I should recompress the pulse. So, generally it is done, what they did, their first thing, they did it in a grating. Generally gratings will give you a negative frequency chirp, and the fiber gave you the positive frequency chirp. So, these two cancel each other and then you can get a compressed pulse. So, that is the duty of the grating pair here. It always comes in pairs. I will explain why. You just think of it as a set of gratings which compresses the pulse. Okay. So, why did not they use another fiber here? Maybe for that particular length you will just get positive, you are not getting a negative frequency chirp. You need something which gives a negative frequency chirp in order to compress back the pulse. So, what I had shown before, remember the chirp was like this, this was the frequency, and so frequency and this is time. So, it was a nice linear chirp. So, the compressor, what it does is, it just makes it opposite. So, this is a frequency and this is a time delay, delta t. So, these two are sort of complementary to each other. Okay, if you give that a different time delay, you give a different delay to those specific frequencies. The frequency on top gets the least delay, the frequency at the bottom gets the maximum delay. So, you are able to compress back the pulse. So, the fiber and this, they are supposed to be complementary to each other. Now, they are complementary to each other, but then this was the first experiment, and of course, it was an ingenious idea, but it was found later on that the pulse that is stretched in a fiber and then compressed in a grating compressor, you never get back the ideal initial seed pulse. The pulse length, and there are some problems in it. They are not really compatible with each other. So, where are the problems? There are certain problems with these two systems which are slightly different from each other. So, later on they found that they can replace this fiber with another pair of grating, but the grating has to be placed in a different kind of way, so that you get a positive chirp. Otherwise, gratings on their own, they always give a negative chirp. So, they did find a way in which a grating pair could be the architecture of the grating pair is such that it is exactly complementary to the parallel grating pair of the compressor. We will discuss about that later, but for the moment this is how this pulse works. Okay. Now, we come to the problem. Originally, for the nanosecond pulse chain, it was chosen, the chosen material was ND glass over carbon dioxide laser. Though carbon dioxide laser had a larger efficiency and the ND glass laser had a lesser efficiency, still ND glass was chosen and the chains were made with ND glass. Okay. Now, here there is another problem. As you can see in ultra short pulses, the bandwidth, the large bandwidth is the main problem in any laser chain. You have to preserve that bandwidth and you have to have large bandwidth. So, here the CO2 laser would be discarded completely. You ccannot get those ultra short pulses in the femtosecond range with a carbon dioxide laser. because it has a very small, very tiny bandwidth. It's a gas laser, so the gas laser lines are almost discrete lines. So the bandwidth is nothing compared to the solid state medium bandwidths, ND glass. I have been speaking of ND glass till now, but then if you really see, there are many gain media which has been developed over time, and so many glass media, as you can see here, are available. Now, how do you know which one to choose? They are all perfectly made. Okay. So, how do you know which one to choose? See, there is chromium LiSAF, okay. There is ytterbium glass, ytterbium YVO4, there is chromium forsythite, chromium YAG, and so many crystals and glasses which have been developed over the years, and all of them have kind of reasonable bandwidth. If you see, the bandwidth here is 30 nanometers, much more than that of glass. Glass full width half maximum of that gain bandwidth or the spectral range is 22 nanometer. Okay. So, out of all this, titanium sapphire, as I told you before, is a very popular system that is used. That's because it has, and especially for femtosecond lasers, that's because it has 180 nanometer bandwidth, which is much more than ND glass. Okay. But then, for that matter, chromium YAG also has 200 nanometer, which is better than titanium sapphire. Then you have 600 nanometer for chromium ZnSe, which is better than titanium sapphire. But then why has titanium sapphire become popular? Why not any of these? Okay. So there has to be some way of choosing this, choosing the kind of glass that you require. Glass or crystal, whatever, this you have to choose that for your amplifiers and for your oscillators. So as I say, the titanium sapphire has become the most popular, though it does not have a bandwidth which is larger than many of the others that I have listed out here. Okay. So all these, now the bandwidth is important because, as I say here delta T delta nu, as I have said before, is 0.32. I have been talking in terms of delta T delta nu is equal to 1, but 0.32, and this number comes from the shape of the pulse. So it could be a secant pulse, it could be a Gaussian pulse. For a Gaussian pulse, it is somewhere around 0.4. For a secant pulse, it is close to 0.32, a sec-h square pulse. It's called secant a pulse. So there is a slight variation from 1 there. So here it is very obvious. You have your delta T will be short if your delta nu is very large. Okay. Delta T is short, delta nu is large. Okay. So we keep looking for the large lasers. But there is one more problem. One more problem is if you just compare ND glass, this is the lifetime. Here I have written as the full width half maximums. This is a full width half maximum of the spectrum, okay, of that medium. And this is the lifetime of the upper lasing level. Okay. So what does the lifetime of an upper lasing level signify? The lifetime signifies that if it is there in the upper lasing level for a longer time, that means it can store the energy that you have done through pumping for a longer and longer time. Okay. The energy can be stored for a longer time, and that is an asset. If, say, by the time the pulse comes in, some of those upper laser levels, they have all tumbled down to the lower laser level, you do not have any gain in the medium for the amplification to take place. Okay. So you can have this upper. So the lifetime of this is large in case of ND glass, and it should not fall down easily. Okay, it should stay there for a longer time. Okay. So, because of that, ND glass is a very important material to have amplification in. Compare that with titanium sapphire, it is 3.2 microseconds. So, it really cannot be used, it is difficult to use it in an amplifier system. Okay. While you see many of these are all short. This is quite large. Ytterbium glass is pretty good. That also can be used as a medium. It has 1300 microseconds. Okay. It is better than ND glass, and it has a good what should I say, bandwidth is better than ND glass. But I think many of these other crystals are used in kind of oscillators, other oscillators, only in an oscillator or in many other kind of lasing system, in fiber lasers. They are definitely used, but not used in a long laser chain that I am describing now. So, what they say is there is a figure of merit for choosing. The figure of merit is sigma tau. Tau is the lifetime, which refers to all this, and sigma is the stimulated emission cross section. Okay. So, the figure of merit is proportional to the stimulated emission cross section and the lifetime. It seems reasonable, isn't it? You want to know the probability of stimulated emission cross section, which is a stimulated emission, which is given by this cross section, and you would like to know how long those molecules which are pumped up here remain there. Okay, so that is given by tau. So, if you take that multiplication, if you take in case of ND glass microsecond centimeter square, it is 1440. While in case of titanium sapphire, it is 131. So, much less than ND glass. So, ND glass scores over titanium sapphire as far as this goes. There are many other problems in a laser chain which you will come across. Cooling systems, much more mundane kind of problems like cooling system, shorter space, and all these are there. But the basic concept, in a basic concept, you know, ND glass is superior to titanium sapphire in many ways, but still titanium sapphire is used in the oscillator to produce the seed pulse, and then in the amplifying medium it is ND glass which is used. Okay. We will go further beyond this in my next lecture.